Now, this video is just to introduce the paper and give you some idea of what's in it. It is a paper in two parts. The first part is about the simultaneous saturation result itself. And the second part is an application of it to a particular K-linear restriction extension problem. I would see this paper as being more about the simultaneous saturation result, in the sense that it isn't so much that I wanted to do a K-linear restriction extension problem, and so I constructed this simultaneous saturation result to apply specifically to this application. Rather, I developed the simultaneous saturation because I wanted to look at a general principle, and this is an application that I'm using it for. So the whole idea of simultaneous saturation is that you just want to control where things are big. Now, this comes up all the time in the kind of work that I do. I work a lot in analysis. I'm often looking at questions about where is T of F big? So T will be some operator applied to a function. Where is this big? How can I control how big this is? And it's often very easy to find a big point. So find one point where T of F is really large. But for the kind of really good information that we want, say, to do an LP norm, we tend to want to know about whether it can be large over a big region. So that's this sort of question is, can I look at the set of points where I saturate? And now an important thing here is you need to saturate for the same function. So one function, multiple points. And this whole principle, the simultaneous saturation, has come out of trying to think about this. Now, there are a couple of sort of innocent observations that you can make. If you're saturating at a set of points, you saturate at any average. Okay, that's fairly standard. And the most basic thing you might do is to put an arithmetic average in there. Okay, this is certainly going to be the case. And you might say, all right, what I could do to try and prove that I can't have too many saturating points is I could compute the average, do some sort of analysis on it, show that it's less than expected, and that would give me that I can't have too many saturating points. However, that's a bit difficult because arithmetic averages are difficult to deal with on multiple points. Firstly, they're not very sensitive to small data. So if you have a lot of large data and one thing that you got wrong, one thing that's small, your average might still be quite big. You might not be able to really pick up that the average is smaller than you expected it to be. Also, particularly for the world that I come from, which involves oscillating things, dealing with sums of oscillating things is really hard. So this is, you've taken a problem and replaced it with a really, really, really hard problem. So what I want to do is instead look at geometric averages. So instead of taking the sum and 1 over n, take the product and the nth power. And certain advantages here. So firstly, they're very sensitive to small values. Okay, if you actually have a 0 value, your whole product goes. If you have a value that is just small, it makes a really substantial effect on the product. So they're more sensitive. It's easier to tell if your average is smaller than it should be. So this is why I wanted to work with products. Okay. It also is handy because you're not dealing with this cancellation of the sum. You're really just asking questions about size. Is the product big? Is it not? And in fact, in this paper, we really only have two sizes. Either it is big or it is practically 0. Okay, so it is a real dichotomy that you ask about. And the idea behind simultaneous saturation is that you're going to measure all of the possible interactions. So you've got a bunch of points. Can I simultaneously saturate? I ask for each pair of points, can I do that? I'm going to record that in a really large energy matrix. You sort of see in section 1.2 how you construct that. The idea then is to create paths of points from that matrix. So for instance, here's a path between a couple of points. Okay, so P sigma 1 and P sigma 100. So if I could pass through those 2 points, And sigma is something that tells me how I reorder my points. Okay, and say I required a connection to sigma 54, then I can put that together as a chain. So these three things could be three separate points, and I'm connecting them together. And the idea is to say, I can't connect too many points together, or I'll have some kind of obstruction. And if I have some kind of obstruction, that will help me control the number of points. You sort of put it two ways. If I've got the obstruction, that bounds the number of points, or alternatively, if I have too many points, I have to be able to construct the obstruction. So here I'm just talking about a specific example, and this is the example that I came in on, and this is thinking about the multilinear extension problem. And here the obstruction is expressed in terms of directions. So you have a bunch of different directions, and it's a fairly standard thing to compute, and you'll see a bit later in the paper, that each of your multilinear extension operators is associated with a direction. And your obstruction is about moving around in d-dimensional space. So the obstruction I use, and I've used in this paper, is geometrical. So you have a bunch of points. Say I'm moving in three-dimensional space, and I move around between 3 points, and I can create a path around those points. And a big part of the proof of the main theorem in this is constructing these paths. So the multilinear extension thing says, I would need that P1 and P2 are connected by the E1 vector pointing in the first direction. P2 and P3 are connected by the E2 direction, and the final two, P1 and P3, are directed by the E3 connection. So here is my obstruction. 3 points in three-dimensional space have to lie in a plane. So there is no way they could be connected up by these three coordinate vectors. So this gives me my obstruction and my limit on my number of points that I can construct. Okay, so this little part is just discussing that in a bit more detail and how you construct these paths. Now, when I do the proof for the simultaneous saturation result, I am going to express it much more generally and express it in terms of conditions. So instead of saying things are connected by a direction, I will say there is a relation between the points. For me, and in this paper, the relation is always geometric, but it's not actually necessary to use a geometric relation. You can have other relations, you could have other obstructions. The main thing is that you have obstructions that form loops, because that is the construction that we do in terms of the paths. So the first part of this paper, the section 1, is just this proof of the simultaneous saturation result. Okay, so that just sets it up, constructs the energy metric, constructs the paths, explains how you produce the sort of the legal paths, the obstructions, and how that limits n. Second half of the paper looks at a very explicit problem, which is a multilinear extension problem where the obstruction is geometric. Okay, and so it applies the simultaneous saturation result to be able to get the correct kind of decay.